Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I continue this section B kind of topical MCQ on topic 4, which is to do with gas laws as well as states of matter, but mostly it's gas laws. They involve the Boyle's law, the Charles law, the Avogadro's law, and the ideal gas law. Okay, so you will know with this section B kind of topical MCQ, we are comparing statements or comparing options, where if all three statements or options are relevant to whatever they're asking, there's option A, B will be 1 and 2, C will be 2 and 3, and D will be just 1 being relevant to whatever they're asking, right? So in this question, you are told that you have a sample of gas, you compress it, okay, so you apply pressure, you compress it by applying pressure, and that's why your pressure increases, because when you apply pressure to gases, you put pressure on them, you make them much closer together, so you compress the gases, right? So the volume changes from 76 cm cube to 20.5 cm cube. So this is about 4 times increase in pressure, and the volume only decreased 3 times. So by applying pressure, you decrease the volume, because Boyle's law in physics, not from A-level, but obviously you study in A-level as well, but from your O-level or IGCSE or GCSE physics, you will have learned that pressure of a gas is inversely proportional to the volume of a gas at constant temperature, which it is at constant temperature here, alright? So that means PV equal to constant. We are given the initial pressure and we're given the initial volume, so we can work out the initial P times V. We can also work out the final P times the final V in the second situation and see whether they have the same value or not, because if they are above the same value, that means they have behaved ideally, because ideal gases follow from Boyle's law. Alright, so that is how you check statement 1, although I should check statement 2 first by logic of these options. Alright, so if I check statement 2, it says the gas partially liquefies. In terms of liquefaction of gases, so you know that when the gaseous molecules get so close together, they become closer together, so you are forming intermolecular forces between them. You will get stronger and stronger because they get closer together. Eventually they will condense into the liquid state. Okay, if you use a butane gas cylinder before, you will have heard of liquefied natural gas. So natural gas being gas, and then you liquefy it by putting it under intense pressure. That is what those metal containers that store the liquefied natural gas basically are used for. They are intensely high pressure and they store your natural gas as a liquid state. And then you get a regulator on top of your gas cylinder, and that regulator basically adjusts the pressure so that when it comes out very slowly, the liquid inside would evaporate or will vaporize straight into gas, and that's what you use for your cooking or for various purposes. This is how liquefied natural gas are also transported across continents to many other countries, from oil or gas producing countries to other countries in the liquefied state, because you reduce the volume a lot. You reduce the volume a lot when you convert from gas to liquid. Here, you increase the pressure by 4 times, but your volume only decreased by 3 times. So yes, your volume decreased, but your volume doesn't decrease by a lot. And you know that in the form of liquid, the liquid will take up so much lesser volume than a gas. So we can't really say that the gas already liquefied, because this volume is still way too big for this much gas to form this much volume. That is not likely at all. Alright, so from that statement alone, I already can justify that 2 is not acceptable. Okay, since this is still quite big, if it does form a liquid, it will have much smaller volume than this, considering the increase in pressure is 4 times and the decrease in volume is only 3 times, whereas it should very easily have been 30 times, 100 times smaller. Okay, if you think about volume of a gas versus volume of liquid, yeah? So 2 is wrong. That means you're only left with 1, which is only D is correct, because only 1 is correct. Okay, it says it behaves non-ideally. Like I said, Boyle's law assumes ideality. So let's check initial before you apply pressure to it. P times V is 1500. Instead of converting the unit into the standard unit used in ideal gas equation. Because I'm not doing ideal gas calculation, I just want to check P times V. So I have used the exact same unit as have been given in the question, but I will just keep the unit as such. So it's kilopascal, cm cube. And then my final PV, basically after I apply pressure, I have 6,000 kilopascal. I multiply by 20.5 cm cube. And I get 123,000 kilopascal cm cube. Okay, not equal. Okay, that is not a very good thing to do. Maybe I should show like that and like that. Okay, so since those values are not equal, going from the initial pressure to the higher pressure, your P times V are not constant because they are not the same. That's why it's non-ideal. So D is correct. Well, I mean statement 1 is correct. Statement 2 is incorrect. Already you knew that only one must be correct. Okay. Then we could go through statement 3. Adsorption is not, that is AD. Okay. So basically sticks form weak intermolecular forces. Form weak intermolecular forces to the walls of the container. Alright, but we are looking for the idea of pressure, the idea of volume, applying pressure. Okay, so this has got nothing to do to explain why the volume decrease as the pressure increase. That might be correct, that might be what happened in reality, but it doesn't explain how the volume changes when the pressure increases. Okay. In this next question, so this is about ideal gas equation. So we know that all of these refer to for the gases. Pressure of the gas, P will be in Pascal or Newton per meter square, because 1 Pascal equal to 1 Newton per meter square. The volume is in meter cube. The molar mass is in gram per mole. The density will be in gram. Density is mass over volume. So you have gram because you have the mass, and then the volume is in meter cube. Alright, because they're expressing it in terms of ideal gas equation. So the volume is in meter cube, so I have to express it in meter cube. The mass is in gram, so I have to express the mass in gram. Molar gas constant is given in the data booklet. It's joule per mole per Kelvin. The temperature must be in Kelvin. Okay, because temperature in degrees Celsius is different from temperature in Kelvin. So where 0 degrees Celsius equal to 273 Kelvin. So anything above 0 degree, you add 273 to it. All right. So looking at option 2, so it says PV equal to big M over RT, and we know that's incorrect because I say M equal to molar mass. This is incorrect. The correct one is PV equal to nRT, where N equal to mass over mR. So this is correct. So that is incorrect, this is correct. And because of the correctness of that should be M over mR RT. Big M here stands for molar mass. Your molar mass is at the bottom, not on the top, and you have M over mR. You don't have just molar mass. Okay, so 2 is incorrect. Really, you're only left with 1 being the correct answer. And they have given you as density times RT over molar mass. The molar mass M there is the mR, and you make pressure the subject. So if I make pressure the subject, I can move M over V times RT over M. That is density. Density is mass over volume. As I have shown you, density is mass over volume. The big M there refer to molar mass, which is just my mR there. 1 is correct. 3 is also incorrect because that is concentration. Concentration would be in mole. Okay. Usually our concentration we express it as mole per dm cube, but because this is in an ideal gas equation, your volume would follow the unit of volume in the ideal gas equation, which is meter cube. So it's mole per meter cube, or you can think about mole over volume. All right, concentration mole over volume. That can't be right because you see your volume is still here. Your mole divided, your mole is mass over mR. Then you have mass, which is not equal to concentration. So you won't be able to get this equation at all. And by logic, we already knew that by checking 2, only 1 is correct because 2 is incorrect. So number 3 is also incorrect. You can play around with rearranging an equation. Even if you follow the unit wouldn't have matched up at all. In this next question, we are dealing with more of the gas laws. So each symbol has its own meaning with their particular own units. So which statements are correct? If I check for 2, the density, we're looking at ideal gas, it's inversely proportional to temperature. So looking for an ideal gas equation, PV equal to nRT, PV equal to mass over mR, RT, make m over v the subject, so I have P mR over RT. This thing is density, because mass over volume, density is mass over volume, okay, the mass per unit volume. So anyway, I don't have to write another one, I just have to equate that to density, because density is mass over volume. So looking at that, I hope you can see density is here, your temperature is there, therefore density is inversely proportional to temperature. So density for an ideal gas from the ideal gas equation, inversely proportional 1 over the temperature in Kelvin, where each symbol has its own usual meaning. The temperature is in Kelvin. So 2 is correct, okay? Number 1, 1 mole of an ideal gas, 1 mole. So N is equal to 1. Occupy the same volume. Occupy the same volume, so N equal to 1 mole under the same conditions of temperature and pressure. So temperature, pressure is constant. You want to see what happened to the volume, right? So PV equal to nRT, but N equal to 1, so PV equal to RT. Then you want to see the volume, so you make volume the subject, so it's RT over P. So we know R is constant because R is molar gas constant. It has a value of 8.31 joule per mole per Kelvin. It's a fixed value from your data booklet. And we say that when you have the same temperature and pressure, so temperature and pressure doesn't change, and this is a molar gas constant, so that volume of 1 mole of gas will be the same. And that is true because if you are at the same temperature and pressure, then you must have the same volume, since this one is constant, and R is constant, okay? So that means, well, it says same, so there's nothing more for me to say really, which I just explained, all right? So 1 is also correct. And then number 3, you know about Charles' law. Charles' law states that the volume of a gas is directly proportional to the temperature of a gas in Kelvin. That's what it says, yeah? And it also said this only happened at constant pressure. So we see in this question, constant pressure is stated. They say that the volume double, but they give you the temperature in degrees Celsius. All right, so work this out in Kelvin. This is 25 plus 273. That is 298 Kelvin. And let's see if it is double or not for the temperature in Kelvin. So 50 plus 273. That is 323 Kelvin. Your volume double if your temperature in Kelvin doubles at constant pressure. But your temperature in Kelvin hasn't doubled. 298 times 2 is not 323 Kelvin. And you're at constant pressure, so your volume will not be double. Alright, so that's incorrect because you need to convert the temperature into Kelvin based on Charles' law, which get translated into, well, which get incorporated into this ideal gas equation. Only 1 and 2 is correct. That's option B. In this question 9, is asking which of these substances have a giant structure. So each of these are in your case study under states of matter. So if we look at number 2, this is back clay found in crockery. So these are what you call, I forgot what you call this already, ceramics. Okay, you consider this as ceramics material. Alright, and ceramics are not just one type of material. Many type of materials are also considered ceramics. Example, MgO, Al2O3, etc, etc. Okay, and these things have very high melting point and boiling point, and we consider structure of ceramic being giant structure because they also involve things like SiO2 as well, which you know that is giant molecular. This is giant ionic and giant ionic. But in essence, if we consider the overall family of ceramics, they all have very high melting point. Okay, that's why they are being used as backclare in crockery because of their high melting point, and that's due to their giant structure. So SiO2 is an example of ceramic, as I mentioned, giant molecular structure. And then P4O10, because that is your 4 phosphorus plus 10 oxygen, each of which has oxidation number of -2, and overall oxidation state is 0, because this is the molecular formula for phosphorus 5 oxide. 4p equal to plus 20, the oxidation state of each phosphorus is plus 5. Your calculator will not show you the plus. Oxidation number have a sign and a value. Okay, so that 5 there refer to phosphorus plus 5, because this is P4O10. Phosphorus 3 oxide is going to be P4O6. Not that it matters, these are simple molecular structure. You will learn more of this in your, or probably you would have learned this already in your general periodicity, which is in topic 9.1, because oxides of the third period element, for which phosphorus is an example of a third period element, is all part of your case study under inorganic chemistry. So there's just 1 and 2 that has giant structure. This is the last question of this 5-question tutorial series, and again it's similar kind of thing. They're asking you on giant structure, but they've swapped the options of the backclare around. So realistically speaking, you should think about what materials they are. As I mentioned in the previous question, these are ceramics that can comprise of Al2O3, MgO, SiO2. So these have different structure. These are giant ionic, these are giant molecular. But the whole idea of ceramic is that they can withstand high temperature or heat, and that means they have very high melting point, and that is all down to giant structure. Whether you're giant molecular or giant ionic, both are giant structure. Calcium is a metal, so we have giant metallic structure, and metals will have high melting and boiling point as a result of giant metallic structure. Okay, calcium oxide, Ca2 plus O2 minus, so you have a giant ionic lattice structure where you have strong ionic interaction, ionic bond between the oppositely charged ion. That will give you very high melting and boiling point as well. So all 3 of these are giant structure. So the answer is A there. Alright. So that's the end of this tutorial, and don't forget to click the button at the bottom right, subscribe to the channel, check out the other topical MCQ playlist as well, and yeah, share the channel with your friends, your class group chat, your juniors and your seniors from school, and anyone else you think this channel might be useful for. And thank you for watching, and thank you for sharing. See you in the next video.